Yeah.
Okay, very good. So, Yanis is currently an assistant professor at um, the Department of Electrical and Systems Engineering at Washington University in St. Louis. He received his degrees from Greece, from University of Patras, and his MS from Duke University. And before joining the university here, he was at actually his MS and PhD from Duke University. And before joining Washington University, he was a postdoc, I believe, at UPenn under the supervision of George Papas. Is that correct? Great. And he has a number of papers that have been recognized with Best Student Paper Award. And I want to list them, but I would like to say that he recently, as of last year, he received the NSF Career Award. And for his work, I believe some of which he will present today. So it's my pleasure to introduce you to Yiannis Kantaros, presenting today for CPSRC and kicking off our seminar series. So Yiannis, the floor is yours.
Perfect. Thank you so much, Ricardo, for the kind introduction, and thanks everyone for joining this talk. It's a really great pleasure to present in your seminar series. And today, the context of the research questions that I will discuss with you comes from the area of safe AI-enabled autonomy. And our vision is that autonomous systems will enable several future technologies and applications that include wildfire management, autonomous monitoring, mapping, surveillance, and probably the most famous application is autonomous driving. And recent advance in computation, sensing, control, AI, and hardware has really accelerated the design of such systems. We have already started seeing impressive demonstrations of robots accomplishing a wide variety of complex tasks. We have seen, for example, humanoid robots assisting humans in manufacturing settings, drones collaborating with each other to build complex structures, or even autonomous cars these days, navigating urban areas and highways. And those videos definitely provide some hope for the future of robotics and autonomy. However, I would argue that those videos are also a little bit misleading. And the reason is because those robots have shortcomings and often make mistakes. And I will say that they make mistakes more often than what we think. So then the question there is why we're not there yet? What is stopping us from making our vision for autonomy a reality? And one of the reasons, among several others, of course, depending on your background, is that those systems rely on deep learning components that are used, for example, for perception, motion prediction, planning, control, and decision making in general. And the problem there is that those deep learning components essentially rely on empirical pattern matching and they are not supported by any correctness, robustness, or performance guarantees in general. And in fact, they are often confidently wrong. For example, in the context of perception and image classification, it has been shown in several works over the past decade that if you make small changes to an image, you can completely fool a neural network. For example, here you have this picture of a panda. You add a very small amount of noise to it, and now your neural network classifies this as a gibbon, and actually it will do so with a very high confidence, 99.3. And similarly, if you place stickers or graffiti on stop signs, you can fool a neural network into thinking that this is a speed limit sign. Large language models like ChatGPT suffer from similar limitations. They're just large neural networks after all. Suppose, for example, that a robot sees through its camera a plastic and a metal ball. And the task for the robot is we ask essentially a language model here to place a ball, one of those two balls, in a microwave. And in this case, the language model will say that the correct decision is to place the metal ball because it can withstand the heat. And now this is not just an incorrect decision, it's actually unsafe. But what is concerning here is that if you take a look at the underlying distribution of tokens, you will see that the language model is several times more confident that the correct decision is to pick the metal ball as opposed to the plastic one. So what I'm really trying to say here through those examples is that those deep learning components lack any kind of reasoning skills. They often don't know what they don't know, and they can operate with high confidence even when they are wrong. And this can compromise safety and performance of systems that rely on those components. Okay, in fact, we have seen several stories in the news talking about failures of autonomous systems because of this overconfidence and broader discussions questioning whether those systems are truly intelligent or not. And now that's exactly my vision and our focus in my group. Our goal is to design introspective AI-enabled robots, robots that are aware of their own limitations, that know what they don't know, and can operate with formal assurances in challenging environments, environments that can be unstructured, dynamic, and unknown. And in those videos, you see some of the platforms we have been using in my group to demonstrate our techniques. You may see some of those videos later as well. Okay, so today we'll cover two topics that lie under this umbrella of safe AI-enabled autonomy. In the first part, I'm going to talk about how to ensure safe autonomy for robots that operate in unknown environments and rely on perceptual feedback that comes from AI-enabled components. And then in the second part, if time permits, I will briefly talk about how we can ensure safe autonomy for language-instructed robots using language models. Okay, so now a key tool that I'm going to use in both parts to provide formal assurances and safety guarantees is conformal prediction. So before diving into the technical details and the actual problems that we're interested in, I would like to spend just a couple of minutes, 2-3 minutes, to provide a brief overview of what conformal prediction is, why it's useful, and later on we're going to see how we use it in those autonomy tasks. Okay, and I will do that through a simple example, a simple image classification example. Here the goal is to predict a label for an image X. Okay, we're given an image, it contains an object, we want to predict the label of the object that is in that image. And we typically address those problems using neural networks, where their input is an image and the output is a softmax vector, which is essentially just confidence values assigned to every single label that our network can recognize. And as I implied earlier, a challenge here is that those neural networks often generate overconfident yet incorrect outputs. Okay, like this is exactly what is happening in this example, where this speed limit sign is classified as a this stop sign is classified as a speed limit sign because the label with the highest confidence value here is the speed limit sign. Okay, so now the question is, instead of predicting a single label, can we generate a set of labels that contain the true label with a user-defined probability? And the answer to this question would have been easy if those softmax scores that we see here in this figure represented true and calibrated probabilities. Okay, however, this is not the case here. And that's exactly where conformal prediction comes in. Okay, so now conformal prediction is just a statistical and distributional and model-free uncertainty quantification framework. It takes 3 inputs. The first one is a pre-trained model, for example, your image classifier, a calibration dataset. Think of it as a collection of images with their corresponding true labels. And these calibration images come from some distribution D, and a failure probability, okay, alpha. And now this distribution D here, we assume that it's unknown. Okay, we don't know the structure of this distribution, but we assume that it is accessible to us, meaning that we can query it whenever we want in order to sample data and construct this calibration dataset. And at test time, given an unseen input, given an unseen image with a known true label that comes from this distribution D, conformal prediction will help us, will construct for us a prediction set C, a set of labels. And now this set has a very nice property that says that this set contains the true label Y with a user-defined probability 1 minus alpha. For example, for this image here, conformal prediction may generate a singleton prediction set that contains the true label with some very high probability 1 minus alpha. And if this object that is in that image becomes ambiguous or occluded, then maybe we're going to get larger prediction sets, which are still guaranteed, though, to contain the true label with a high probability. Okay, so what conformal prediction does is that it just gives us a set of reliable possibilities, but does not tell us how to use those prediction sets. Okay, maybe you're not happy with such a large prediction set, but that's a different story how to use it for decision making. Okay, so now let me try to demystify a little bit conformal prediction and tell you how exactly it constructs those sets. And the algorithm is actually quite simple, at least in the context of image classification. The first step is that we have to construct a calibration dataset. Again, think of it as a collection of images and X and corresponding labels Y. The second step is that now we have to define a non-conformity score, essentially a score that models the error of the model. And then we have to compute this score, this error, for all calibration images. For example, in the context of image classification, typically this score is defined as 1 minus the softmax score assigned by our model F to the true label Y. Okay? For example, here in this example, the non-conformity score associated with this stop sign image is 1 minus 0.2, because 0.2 is the confidence score, the softmax score assigned by our model to the true label, the stop sign. Okay, so this score is 0.8. The larger the score, the worse the performance of our model on that specific example. Okay, and we compute these scores for all calibration data points. And once we do that, we compute the 1 minus alpha quantile of those scores. Okay, and we're going to denote this quantile by Q. And now this is all happening offline before you deploy your system in the real world. Okay, so now at test time, you are given a new data point, a new image, which has an unknown label. And conformal prediction here will construct this set C that contains all labels Y, for which the softmax score of the model associated with those labels Y is greater than this threshold 1 minus Q. Okay, now this set is supported by that coverage guarantee that I mentioned earlier. It contains the true label with some high probability. And this guarantee essentially relies on the assumption, on the exchangeability assumption, the idea that calibration data points and test data points come from the same distribution. Okay. Okay. Now that we have discussed a little bit what conformal prediction is, and you have a rough idea of how it works and what kind of output it generates, let's go back to our research topics. And as I said earlier, the first part I will talk about our work on safe planning in unknown environments for robots that rely on perceptual feedback that comes from some deep learning components. And we will see how we can use conformal prediction to provide some assurance guarantees and safety guarantees for our system. Okay, so first of all, what is a planning problem? To make sure we're all on the same page. So typically in a planning problem, the goal is to design dynamically feasible paths for our system. Think of it as a sequence of waypoints or sequence of control inputs that will enable our system to reach a desired location B, starting from some initial state A, while avoiding obstacles, okay, or unsafe regions in general. And over the past few years, there has been a long list of works on how to design safe planners and controllers. But moving forward, as we start sending autonomous systems in the real world, a challenge that we will have to start addressing is that the environment is unknown. Okay, often our robots will have to complete tasks that require them to reason about the unknown geometric and semantic structure of the environment. For example, in a fire extinguishing scenario, robots may have to extinguish house fires and tree fires, and while always keeping a safe distance of at least 5 feet from phone poles, 10 feet from trees, 20 feet from people, and so on. Okay, so depending on both the location and the label of objects and agents that our robot encounters, it has to adopt a different behavior. So now, successfully completing such tasks requires a tight integration between the perceptual stack and the decision-making layer. Depending on what we see, we have to make decisions accordingly. And of course, there has been, again, a long list of works here trying to address problems along these lines. The key limitation that we see here is that those works essentially rely on some heuristics or on empirical validation, and they typically lack some sort of correctness guarantees. So here, the fundamental research question that we want to address is how can we design paths for our system, plans for our systems that will allow them to safely complete their tasks with some user-defined probability 1 minus alpha in the presence of perceptual imperfections, perceptual uncertainty, and overconfidence issues like the ones that I mentioned earlier today. So that's the high-level goal. That's the high-level goal for the first part of this talk. So let me try to formalize a little bit more this problem. So here we assume that we have a robot governed by some discrete time dynamics, where P of t is the state, think of it as position and heading, U of t is the control input at time t, like linear and angular velocities. And our robot operates in an unknown environment. Okay, it operates in an environment that is populated with some semantic objects and regions. Each one of them is characterized by their position and their semantic label, like the environment that you see on the figure here. And our robot has to complete a task, a reach avoid task that is defined over those objects and regions. Okay. For example, our robot may have to extinguish to reach a goal location or an object while keeping a safe distance, dk, from objects and regions of label k. Okay. For example, maybe our robot has to extinguish here the house fire while keeping a distance of 10 feet from people, 5 feet from trees, and 3 feet from phone poles and cars. And the challenge here is that the location and label of those objects and regions is unknown. Okay, if it was known, we could use existing autonomy architectures to solve this problem. Instead, our robot relies on some AI-enabled perception system to detect, localize, and classify objects that it encounters. Think here of depth cameras and semantic segmentation algorithms. Okay, and you can see this figure on the right side here visualizes the output of such a perception system here. The depth image gives us range information, how far objects are from us, and the segmented image gives us information about what those objects are. Okay, every single pixel in this image is classified, and every single color here corresponds to a specific label. For example, the purple color corresponds to a tree. Okay, now this perception system can be imperfect, noisy, and in general, it may generate unreliable outputs. So then our goal now is to compute a path for our system. You can think of it as a sequence of robot states so that the task phi that we have assigned to our robot is completed with a user-specified probability 1 minus alpha. And again, the reason why we have this probabilistic satisfaction is because of perceptual uncertainty. Now, here there are two main challenges that we have to address to tackle this problem. The first one is, how do we model perceptual uncertainty? How do we model perceptual uncertainty? If you noticed on the previous slide, I didn't make any assumptions about the sensor models, noise characteristics, and so on. I only say that the perception system can be noisy and imperfect. Okay, so the question here is, how can we reason about those perceptual imperfections? And the second challenge, once we figure out how to address the first one, is how to use this modeling result, this perceptual uncertainty, for decision making in a way that will allow us to do probabilistically correct planning and provide some assurances for our system. So these are the main two challenges that I will be addressing over the next few minutes. Okay, so now this is the autonomy architecture that we have been building in my group to address this kind of problems. It has four main components. The first component is the perception system that I mentioned earlier today. It generates depth images, segmented images, and so on. The second component is a mapping box or a SLAM algorithm that fuses over time those measurements and generates a map of the environment, a belief about what the environment looks like. And here I want to say that those two boxes, perception and mapping, are fairly standard in most autonomy architectures. Okay, there is nothing really fundamentally new in this architecture so far. But what is new is this uncertainty quantification box, which essentially tries to quantify perceptual uncertainty. Or to be more accurate here, it tries to quantify how certain we are that the map that we have built so far is the correct one, is the accurate representation of the true environment that we live in. Okay, and as you can guess here that we are going to use ideas from conformal prediction to design this box. And now the out of this box, as we'll see later on, is essentially a set of maps. Okay, and this set will have a nice property saying that it contains the true map with some very high probability. And then we have the fourth box here, the fourth component, the planning layer, that takes as an input this set of maps along with some task specification and safety requirements. And then it generates the next state that our system has to reach. Okay, and of course, we close the loop here with our robot. The robot will navigate towards this next state, will collect more measurements, update the map, and this keeps going on until we complete our task. Okay, so I will not have time to tell you what this mapping algorithm does. This falls a little bit out of the scope of my talk today, but I will tell you what this map looks like, and later on we're going to see how we can use it for decision making. Okay, so you can think of this map as a multi-class grid map, or in other words, as a collection of cells, as you see in this figure, where here each cell is modeled as a random variable, and the probability as a discrete random variable, and the probability mass function of this random variable gives us the probability that the cell J is occupied by an object of label K. For example, if you focus on this cell here that I have highlighted, this cell is associated with this probability mass function. And according to this probability mass function, the most likely label of the object that occupies this cell is the red one, okay, that corresponds to a human. Okay, and this video here shows what a map of an outer environment looks like when it's built online. Okay, so now here you may be wondering, okay, can we use those probability mass functions to address the challenge that I mentioned earlier, to model perceptual and mapping uncertainty? And the answer is that we cannot really do that. It's not entirely correct to use those mass functions to model uncertainty. There are two reasons for that. The first one is that those mass functions have been constructed by fusing through Bayesian updates the confidence scores of AI-based perception systems. Okay, and as we said earlier, those confidence scores do not represent true probabilities. So if you fuse them, you will not get true probabilities either. The other reason is that those mass functions have been designed by using some strong modeling assumptions about the sensor models and noise characteristics, for example, Gaussian noise, that may not hold in practice. So what I'm trying to say here is that uncertainty metrics that come from such mapping algorithms are not really reliable. They don't represent true calibrated probabilities, and therefore we cannot really use them directly for probabilistically correct planning and to provide some assurance guarantees for our system. Okay, so then the question is, then how can we quantify the perceptual and mapping uncertainty without making any assumptions on the sensor model, noise characteristics, or outputs of our AI-based perception systems? Okay, that's what we're going to talk about next. And as you can guess, the key idea here is to use conformal prediction. That's why I introduced it earlier. Earlier, I showed how we can use conformal prediction to quantify uncertainty of an image classifier. Now we're going to see how to use conformal prediction to quantify uncertainty of a mapping algorithm. Okay, the input to such a mapping algorithm are measurements like depth and segmented images, the previous map, and the output is the next map that we get after we've used those measurements. So now if we apply conformal prediction, and we'll see how to do it on the next slide, so please bear with me for a minute. If we apply conformal prediction, here the uncertainty quantification outcome that we're going to get looks like the following. So for each cell J in the map, we are going to, given, let's say that the map is this, M of t, then for each cell J in the map, we are going to construct a set of labels, and this set contains all labels K that our system can recognize that satisfy this inequality here. So this P of t is the probability mass function that comes from our mapping module. And so this is the probability that cell J is occupied by an object of label K, according to our mapping module. And if this probability is above some threshold Q, then we include that label to our prediction set. Okay, and again, this Q, this threshold Q, will be computed using conformal prediction. Don't worry about it. We will talk about it on the next slide. Okay, and just to visualize a little bit what is happening here, let's say that we have the environment that you see in the bottom left corner, and the map that we have built using our mapping module looks like something like this, okay? Where you can see here that the person, the human here, is misclassified as a tree. And actually this happened in this case because the person is quite close to the trees and there are some occlusions for our robot. So instead of confidently misclassifying the person here as a tree, conformal prediction will build a set of labels and it will tell us that this cell J is either a tree or a human. Okay, I don't know which one, but it's one of them with some high probability. Okay, and this is not a made-up example or a hypothetical scenario. It's based on some simulated data that we generated in a photorealistic simulator in Gazebo. Okay, so now let me tell you a little bit about how we build those sets, and then we're going to see what exactly is the guarantee that we get using conformal prediction. So the steps that we follow to construct those sets are very similar to the steps that we followed in the image classification example. So it all starts with a calibration dataset. We have a set of calibration environments that come from some distribution D. The next step is that we have to define now a non-conformity score for our mapping algorithm, and we want that score to model the mapping error. The challenge here, which didn't really exist in the image classification example, is that there are time dependencies. So if you take a look at the input-output structure of the mapping algorithm, the output here of the mapping algorithm depends on the previous map, okay? And not only does it depend on the previous map, but it actually depends on the paths that your robot has followed to collect those measurements and build those maps, okay? So there are some strong time dependencies here. So that's why here we define the non-conformity score so that it models the worst case mapping error, okay, the worst case error of our algorithm across all maps that our robot can construct in that environment. Okay, so to be a little bit more accurate here and a little bit more technical, that's how we define the mapping error. So the red term within the parentheses models the mapping error at a very specific cell J, at a very specific time step t, once our robot has followed a fixed path. Okay, and now we have this maximum operator here that computes the worst case error. It's the worst case error across all cells J, all time steps t, and all possible paths that our system can follow. Okay, I have to acknowledge here that computing this score is computationally challenging because of this maximum operation that we have to apply. Okay, so in practice, we approximately compute it, and we can discuss this offline if you are interested in. Then we compute this score for all calibration environments. We compute the 1 minus alpha quantile. Let's call it Q. And again, all this is happening offline before you deploy the robot. And you do it once, and you can you're going to use this quantile at test time. So now at test time, when we deploy the robot in an unknown environment, at every time step t, and for every cell J in the map, our robot will build this prediction set that I defined earlier, this set of labels that I defined earlier. And now if you're wondering what exactly is the assurance guarantee that we get out of this complex math here, the guarantee is actually a strong distribution-free mapping guarantee. What it says, informally at least, is that all prediction sets that our robot will build for all cells and all time steps that the robot will build as it navigates the environment will jointly contain the true labels with some high probability 1 minus alpha. Okay. And observe here that this guarantee holds regardless of what the task of the robot is or what path and measurements the robot has followed to build those prediction sets. So the result is quite general and can be applied to any autonomy task that you are going to assign to your robot. And another thing that I want to highlight and make it clear is that this probabilistic guarantee does not hold for a specific cell or for a specific time step, but it holds jointly for all prediction sets that you may construct. Okay, as your robot navigates the environment. Okay, so now that we have seen how to quantify mapping uncertainty, and we have seen what exactly this uncertainty quantification outcome looks like, the next question is, how do we use this capability, this uncertainty quantification capability? And this becomes particularly challenging in case of ambiguity. Okay, how should our robot behave if conformal prediction tells us that our robot is surrounded by either trees or cars or people? Okay, so how can we design plans in case of ambiguity? The approach that we take here is a conservative one. Okay, so the intuitive idea is that among all the labels that are included in those prediction sets, we're going to pick the worst case one. Okay, and this will give rise to a worst case map. And then our planner here will make decisions based on the worst case scenario. Okay, so let me try to explain, to elaborate a little bit more what I mean by worst case labels and worst case maps. And let's do that through a simple example. So let's say that we have built a map that you see here on the left side of this slide. And let's focus on this cell here that is highlighted. So now here, conformal prediction, let's say that it will generate a set that contains two labels, the red one and the purple, okay, human and tree. And now to pick the worst case label, we have to inspect our safety specification, okay? Let's say that our safety specification says that we have to keep a distance of 5 meters from a human and 10 meters from a tree. So here, the label that has the strictest safety constraint is the purple one, the tree. So we're going to pick that one as our worst case label, and we're going to relabel that cell from red to purple, okay? And we do that for all cells in the map. So this will give rise to this worst case map. Okay, those disks that I'm plotting here are essentially the safety distances, the distance from each cell that the robot has to keep based on the assigned label. Okay, so the next question, the next part now is to see how can we do planning given those worst case maps. And conceptually, what we want to do now is to compute a path for our system. We want to solve essentially the optimization problem that you see on this slide, okay? We want to compute a path that minimizes some motion cost function like travel distance. We want this path to respect those safety requirements based on the worst case map, meaning that we have to keep some safe distances from objects around us. We have to respect our system dynamics, and of course, we want eventually to complete our task to reach some goal region. And you can solve this problem using your favorite solver, your favorite planner, A star, RRT, SST. It's up to you, okay? There is nothing really fundamentally new in this optimization problem. So if this problem is feasible, our planner here will return a solution, will return a path, a sequence of robot states. And once it does that, our robot will move towards the next state, this P with subscript T+1. The robot will go there. It will collect measurements, update the map, and then we keep replanning in an MPC style, okay? Now, the challenge is that it's possible that the worst case map that we have built is rather conservative to the point that a solution to the planning problem that I discussed earlier does not exist, even though a feasible path exists in the underlying true environment. So what is happening here is that we switch from this exploitation mode, this planning mode, to an exploration mode. So what we do in this mode is that we compute now the next waypoint of the robot in the free space by solving a safe active exploration problem. We use here existing active information gathering algorithms that we have used in my group that try to mitigate environmental uncertainty by optimizing some information theoretic metrics like mutual information, while always remaining in the free space, okay? And our robot remains in this exploration mode until the planning problem that I defined earlier becomes feasible. And if we do that, we get a nice guarantee that says that the path that our robot will follow during the exploitation and the exploration mode will successfully and safely complete the task with a user-defined probability 1 minus alpha. Okay, and the proof to this result is actually very simple. It relies on the mapping guarantee that I introduced earlier. So what I want to emphasize also here is that this guarantee here does not hold in isolation for the planning box, but it holds for the entire closed loop system as the robot perceives, plans, acts, and explores. Okay, so it holds for the entire, for the closed loop system. Okay, we also run some statistical experiments to validate those theoretical claims. So here we consider 100 mission scenarios in randomly generated environments populated with trees, cars, trucks, and humans. And the results are summarized in this table. In the left column, you see the success rate that we have set, 1 minus alpha, that is 85, 90, and 95. In the third column, you see the mapping success rate, meaning that it's the percentage of scenarios where all prediction sets that our robot constructed as it navigated the environment contain the true label. The fourth column is the mission completion rate. It's the percentage of cases where the path that our robot executed completed the assigned task safely with respect to the ground truth environment, the unknown ground truth environment. And what we see here is that those success rates are always above that threshold 1 minus alpha as predicted by our theory. The only exception is in the 95% case. The reason why this is happening is because of finiteness of our data. Okay, so if we collect, if we collect more data points, more scenarios, you will see that this number keeps converging more and more, closer and closer to 95. The higher the 1 minus alpha, the more data you need to statistically validate those claims. And another interesting observation here is that as you increase 1 minus alpha, the amount of time that the robot spent in exploring the environment keeps increasing. Okay, this is shown on the last column here. And this intuitively makes sense because as we increase 1 minus alpha, the success rate, we are asking the robot to become more and more cautious before committing to a plan. Okay, and that also leads to paths of to longer paths. Okay. Now we also consider a couple of other baselines here. The first one is what we call an uncertainty-informed baseline. This baseline treats the probability mass functions that are generated by the mapping module as true probabilities. Okay, there is no conformal prediction there. And what we see here is that this method performs worse than our method in terms of the success rates. And the reason why this is happening is because it uses heuristic uncertainty metrics. Okay. And the last baseline is an uncertainty agnostic baseline where each cell in the map has the most likely label according to those probability mass functions that our mapping module has generated. Okay. And we see here that this method performs even worse. And again, the reason for that is because it completely neglects perceptual and mapping uncertainty. Okay, it uses point estimates. So what I'm trying to say here is that our method allows us to achieve desired mission completion rates in the presence of perceptual uncertainty. The price that we have to pay here is that our robots will follow longer paths, if you see here in this column. And the reason why this is happening is because we make decisions based on the worst case scenario, based on the worst case map. We also have some demonstrations to visualize how this algorithm may look like in the real world. So the task here of this robot, this is a jackal robot from ClearPath. The goal of the robot is to reach the green region that you see in this environment, while keeping a safe distance from objects that it encounters in the environment. The safe distance depends on the label of those objects and agents. So these red areas represent the unsafe zones. Okay, the robot knows nothing about the location of those objects. Instead, it has a camera and a segmentation algorithm to detect objects. And here the success rate is 0.85, which is relatively low. And that's why here our robot follows a somewhat aggressive behavior in the sense that it never explores. Okay, so it just follows the path generated by a star, I think, towards the goal region. Now, if you increase now the success rate from 0.85 to 0.89, we're going to start seeing some more conservative behaviors where at some point, as our robot navigates the environment, it will realize that there is no solution, at least based on the worst case map that we have built, okay? And this is when it switches to exploration mode, okay? Which is happening right now. The robot starts looking around to collect more perceptual data and become more confident about what the environment looks like. And once it figures out that there exists a path towards the goal region, it uses a star, for example, to compute a path towards the green region. We're going to see some hardware experiments later on at the end of the talk. Now, before wrapping up the first part of the talk, I want to very briefly summarize some other directions that we're pursuing in parallel. The first one is that we're considering dynamic environments. In the first part of the talk, I assumed that the environment was static, which is not always the case in practice. So here we have to reason about future intentions of those moving agents. Okay, that's what is happening in the top left corner. In the top right corner, we consider missions and safety specifications that change over time. And the key challenge here is to see how to resolve conflicts, logical conflicts, that may arise between previous safety requirements and new safety requirements. In the bottom right corner, this is another work that we're considering. This is in a multi-agent setting where some of our robots may fail unexpectedly, and we want to see how the remaining ones can adapt to those failures to complete the assigned task. And the last extension here, the last direction that you see in the bottom right corner is to focus on cases where the task is infeasible, not because of perceptual uncertainty or anything like that, but because of the structure of the environment. Okay. And here the solutions that we are pursuing here is to see how can we physically interact with the environment, how can we enable the robot to rearrange the structure of the environment to complete to make the infeasible task feasible. Okay, to sum up here, we have proposed a new autonomy architecture to integrate AI-enabled perception system with planning and control. We showed that our architecture is supported by some probabilistic assurance guarantees, and our code is also available in case you want to take a look at it. A limitation that our method has is that all these nice guarantees that I talked about hold under an IID assumption, an assumption that says that calibration environments and test environments have to come from the same distribution. Okay, I have to acknowledge here that this is an assumption that can be difficult to enforce in the real world. So relaxing this assumption is something that we're actively working on using ideas from online and adaptive conformal prediction. And these are some references related to the work that I presented in the first part. Okay. In the remaining time, I will talk very briefly about another project that we have started working on, which is on safe conversational autonomy. So in the first part of the talk, I said that one of the inputs to our planning layer here is a task specification. And typically in robotics, we specify tasks and safety requirements for our systems using formal languages like linear temporal logic, LTL. LTL is a formal type of logic that consists of Boolean operators, temporal operators that are defined over Boolean variables. Okay, it's a very powerful tool because it allows us to specify complex tasks in a rigorous and an ambiguous way. Okay, you see some examples of such tasks here on this slide. The problem here is that such formal languages like LTL are not really user-friendly. If you have worked on formal methods, you know what I mean. They require a lot of user effort and expertise to correctly define the task that you have in mind as an LTL formula. So the question here that we had was, can we automate this process of going from natural language commands to temporal logic specifications automatically? And the answer to this question is that we can use language models that are pretty good at processing natural language. And in fact, there have been a couple of works over the last 1 or 2 years that try to solve this translation problem automatically. The problem here, the issue that we identify, is that those methods lack correctness guarantees. Language models, as I mentioned at the very beginning of the talk, tend to hallucinate, generate overconfident outputs, and often wrong outputs. And we think that this is an important limitation because consider a scenario where the temporal logic specification that your language model generates does not accurately represent your natural language commands. So in this case, your system will try to complete something that is different from what you specified. So then the research question that we are trying to address here is the following. We want to see how can we design out translators from natural language to temporal logic specifications that are supported by some correctness guarantees that can ensure that the generated formula is an accurate representation of the natural language command with some high probability 1 minus alpha. Okay. I have a little bit of time, so I will try to briefly formalize the problem and give you the rough idea, the key idea of our techniques here. So here we consider a robot. This robot has a set of known skills that can refer to sensing, mobility, manipulation, and so on. And our robot operates in an environment that is populated with some semantic objects and regions, exactly as we defined it in the first part of the talk. And our robot has to complete a natural language task that is grounded on those skills, meaning that the task can be completed if the robot applies a sequence of actions selected from this set A to some of the objects in the environment. Okay, or more formally here, we define translation scenarios that consist of natural language commands and a set of skills for our robot. We assume that those scenarios come from some distribution that is unknown, but it's accessible to us, and we can sample IID scenarios. And of course, we focus on cases, on natural language commands that can be mapped to a temporal logic formula. Okay, so then formally here, the problem that we want to solve is the following. We want to use pre-trained language models to design a translator so that given any translation problem that comes from this distribution D, the probability that our translator will generate a semantically equivalent temporal logic formula phi is greater than a user-specified threshold 1 minus alpha. Okay, so now let me give you the key idea, how we're going to do that. Let's say now that this blue bar is our translation success rate. What we want to do is that we want to push the success rate above some threshold 1 minus alpha. So how can we do that? We don't do any kind of fine-tuning or anything like that. The key idea is to use uncertainty quantification tools like conformal prediction to quantify uncertainty of our language model as it tries to complete the translation task. And now, in cases where it's not confident enough, based on that threshold 1 minus alpha, about its predictions, its responses, we're going to allow our language model to ask for some help. Initially, this help can come from an auxiliary LLM. Roughly speaking, this auxiliary LLM will also try to perform the same translation task while also quantifying its uncertainty. So then what we're going to do is that we are going to fuse those uncertainty quantification outcomes from the main and the auxiliary language model. And if we're still uncertain about what the correct response is, we're going to ask for feedback from a user. You can also ask from another language model, but at some point you may need to resort to a user. And of course, here a secondary goal is that we want to minimize help rate. This is important, especially if a user is involved in this structure. So we have developed here a tool that we call conformal NL to LTL that can achieve desired translation success rates. I will skip the rest of the slide for the sake of time. I will just show you some statistical experiments that we have run to validate those theoretical claims that we can achieve desired translation success rates. So here we consider 1,000 scenarios of varying complexity. We use GPT-4 as the main language model that will do the translation. And we use DeepSeek as the auxiliary LLM that will provide feedback whenever needed. And both are pre-trained, okay? We haven't fine-tuned them. And we set this success rate 1 minus alpha to various thresholds, 95, 97, 99%. We run here multiple experiments, statistical experiments, and we can see that this success rate is always above that threshold 1 minus alpha, while keeping the help rate quite low, especially from users. It's always less than 0.5%. And as you can see, as you increase 1 minus alpha, the help rate tends to increase, which makes sense. And interesting, I think, parallelism to the first part of the talk is that here, whenever our system is uncertain, it asks for help. It coordinates with other agents, other LLMs, or a user. In the first part of the talk, whenever it was uncertain, it was switching to exploration to collect more perceptual data. So the high-level idea is the same. Whenever you are uncertain, you ask for help or you actively collect more data. Now, an ongoing effort in my group is to try to integrate those the software and those architectures that we have been building. So offline here, we have the translation algorithm that takes us an input natural language commands. It generates some temporal logic specification that is then being processed by the autonomy architecture that we saw on the previous slide. And
deliver this to person who is probably in large disk.
We have some experiments to demonstrate those capabilities. So here the task of this quadruped is to deliver a chocolate bar that you see on top of the robot here to a person who is probably in the large desk here and less likely in the kitchen. Okay, so the robot here, this command is translated to a temporal logic specification that is then processed by our navigation stack. So what is interesting here is that the robot initially, if you observe that the robot initially heads to the desk, and then it doesn't find the person, and then it switches back to the kitchen. The reason why, where it will find the person, the task will be completed. The reason why it goes to the desk first is because the natural language command, at least the way that it's phrased here, it creates some implicit prior about the location of the human. Okay, if the human is in the desk, then the robot will okay, here the robot will go to the desk, it will find the human, and then the task will be completed and the mission terminates. We have more experiments.
Mark the damaged cars by taking.
We have more experiments in the mini city platform that we have at WASU. This is a 3D mini city. It's a 1/8 scale physical environments. The dimensions here are 90 feet by 30 feet. It's actually quite massive test bed. And the task here of the robot is to place traffic cones next to damaged cars, like the blue car here and the red car that you see over here. We have more experiments here in this mini city. We are slowly starting moving towards outdoor experiments. I'm happy to discuss those more offline. I will conclude by saying that here we've developed a translation algorithm. It's supported by some translation success rate guarantees. Our code is available if you want to take a look. Also, our algorithm can be coupled with both open and closed source language models like ChatGPT or Llama models. And the same ideas can be also transferred to cases where you want to use your language model, not as a translator, but as a planner directly. Okay. Of course, I want to thank all of my PhD students. This is effort that has been led by them. And of course, my collaborators from Penn, UCSD, WASU, and USC. And if you have any questions, I will be happy to take them. I hope we have some time.
Thank you, Yiannis. I think Professor Ricardo had to leave. But yeah, we have a couple of minutes for questions. I personally have one.
Yep.
Well, you kind of talked about it, but in the conformal prediction part, could you please elaborate more how you're thinking on this, exchangeability assumption? I've read a couple of works where they consider the distribution shift between your calibration and your training data set, but yeah, great if you just can elaborate a little bit more, that's interesting.
Okay, I don't know what happened. Let's see. Okay, so let's see if I can go back to that slide. Okay, perfect. So yeah, so here this is a fundamental assumption in conformal prediction that says that calibration and test environments come from some distribution D. You don't know what this distribution looks like, but you assume that they come from the same distribution. Now, as I said earlier, this is not an easy assumption to enforce in practice. For example, let's say that you have a calibration data set with images taken during the day, okay? But in the real world, images can come during the day or during night or when it snows or when it rains or when it's foggy. In this case, the guarantees will not hold if there is such distribution shifts. One approach to address this issue is to use one is robust conformal prediction. The idea there is, is that instead of computing here the 1 minus alpha quantile of those scores, you are going to compute a worst case quantile. You are going to say that I'm going to consider all distributions that are within some, let's say, distance, epsilon, from this nominal distribution D. And based on that distance epsilon, I will compute a worst case quantile that can account for those epsilon distribution shifts. Okay, that's one approach. Another one is adaptive conformal prediction that makes no assumptions about distributions, that you may have arbitrarily large distribution sets. And then in that case, this quantile 1 minus alpha keeps, we update it online at test time in order to minimize any kind of error. The drawback of such an approach of adaptive conformal prediction, where you completely relax all assumptions, is that your prediction sets will become very conservative. It's very likely that the sets that you're going to get are going to be very, very large. And this is not very nice because, for example, in the context of the first part of the talk that I presented, this may mean that your robot will keep exploring for a very long time just to account for this conservatism. So that's the drawback there. You can relax all these distributional assumptions, exchangeability and IID. The price that you're going to pay most likely is that the behaviors that your robot will exhibit will be very, very conservative. Did I answer your questions?
Yeah. So I was only aware of the robust conformal prediction, but this adaptive one is interesting. So if I get it right, you're basically computing the quantiles all over again. How computationally expensive is that? Because then to compute the quantiles, you need to organize, sort, and so probably while you do all that, no.
Right, that's a good point. So at least in the vanilla conformal prediction, the way that we have applied it here, the main bottleneck is that you have to construct the calibration datasets. You have to compute those scores. This is, depending on the application, this can be computationally challenging. Here for this image classification problem, it's not that difficult, but in the planning problem I mentioned earlier, it can become quite challenging because of how we define the conformity score. So in a simple example like this image classification example, this is it's computationally straightforward, let's say, to compute those quantiles. In other more complex problems like the planning one, it can get a little bit tricky. So if you want to use adaptive conformal prediction where this quantile keeps changing, I think it can be a little bit computationally expensive. I have to admit that I haven't applied adaptive conformal prediction, so all I'm doing right now is give you educated guesses, and I could be wrong. But it's likely that adaptive conformal prediction could become a little bit more expensive because you need to keep computing quantiles on the fly.
Yeah, perfect. Thank you, Yiannis.
Thank you.
Nice work.
Thank you.
Okay.
I as an old dinosaur from the prehistoric days of control systems, am much more a continuous rather than discrete type person. And as a matter of fact, I just hate to program. But so anyway, I'm just warning you ahead of time who you're talking with. And what I'm to make more clear your point on this is really this is boiling down to my mind essentially to Richard Bellman's old ideas of the curse of dimensionality, that eventually through the quantification of now you call it path planning, and your whole approach to this is path planning. To my mind, that means trajectories.
Mm-hmm.
And I'll think about trajectories in state space. And this is any dynamic system, whether it's dynamic or discrete, right? So then what Richard Bellman came up with something he called the curse of dimensionality, which is you eventually, if you're going to look at every pixel on a photograph, if you're going to consider every possible instant of time, then the time to compute the operations that the computer has to go through, even if you've got a computer at terahertz per second data operating system, it will eventually heat up and explode. So there comes a limit where I don't think we can come into a completely discrete space. In other words, we really have to assume things like continuity, differentiability, and in my mind, at least some kind of observability assumptions, some kind of probability that we have to look at whether the probability that we are computing is indeed a probability function or not, whether it has a variance that is non-negative definite. Stuff like this has to go into it. But even worse, in any practical feedback control system, you have to, even with artificial intelligence and machine learning, you have to use what I call the SIME paradigm. S, it must reduce to something that is scientifically valid. I, it must have some form of imagination. M, it must have morality. It must somehow be adjusted to what humans think is moral. And I, E, it has to resolve itself with past experience. That's it. I'm sorry, I soapbox.
No, this is a valid point actually, and you know, going back to what you said earlier, there are scalability limits here. I'm not claiming that this can scale to arbitrarily large.
This is wonderful. I mean, your approach is great. You exactly put focus on the things that are possible.
Yes, Yeah, but I really want to make it clear that, there are indeed limitations there. Like, for example, when later on we apply here conformal prediction to quantify uncertainty, this approach may not scale to very large maps with millions of cells in that map. So there are issues with, cares of dimensionality challenges here as well. But I do agree with your points that you raised there.
Thank you.
Do you have any other questions, probably in the Zoom room, online?
I actually have one question. Professor, since you talk, and can you go back to where you define the non-conformity score, the formula?
Mm-hmm.
So so for this one, is that assumed for all paths and time step and cells you this is the assumption of this maximum?
Can you say it again? You said if this is the maximum overall paths, is what you asked?
Yes.
Yes, that's true.
But in reality, we cannot get
Correct.
all positive, right? How sensitive is this overall convergence guarantee?
Correct. This is a beautiful comment. You're absolutely right that this set P here is the collection of all possible paths. It is an infinite path in general. So in practice, when we implement this, we create a finite set that has a finite set of paths. So this theoretical guarantee that we get here holds only if you compute those non-conformity scores accurately. In practice, there is a gap here. There is an approximation gap that, unfortunately, I cannot really characterize. What happens if this set P here is some sort of a discrete, finite set? But you're absolutely right. And that's why it's computationally expensive to intractable, actually, to compute this score. So we do approximations to account for that.
Oh, okay. Thank you very much.
Thank you. Any other questions?
That's very nice because it would be nice to be able to look at some steady state solution.
Yeah.
As it goes to infinity, what is the
Yeah. Because currently I'm exploring there's some work combining temporal specification with dynamical system, and in the end it comes to be a hybrid system, and we can maybe show some convergence results in this combining the discrete and continuous system. So yeah, this is currently exploring.
Will you send me that paper? I would love to take a look at that.
Yeah, of course. I'll send you to your email.
Yeah, perfect. But I agree with you. Ideally here, it will be interesting to see, to somehow characterize this gap and see what happens as the size of the set increases and how this approximation gap behaves as the size of this set changes. This is indeed a good point.
I guess what I'm saying is that it's maybe possible to compute the steady state solutions ahead of time.
Yeah. Thank you.
Well, if there are not any other questions, thank you, Yiannis, once more for your talk. Really
Thanks for your time. And again, I really appreciate the invitation, and it has been a great pleasure to present in your seminar series. I really appreciate it.
Of course.
Thank you, Yiannis.
I think you have one-on-one meetings after, right?
Yeah.
Probably we can take, or you can take like a 10-minute breather and.
No, I don't need a break. I'm fine. I mean, if I'm happy to join on Zoom call.
I would say, can they use the same?
Yeah, they can stay on. Do you know who's up first?
Daniel.
Okay,
So I think Daniel's there. So yeah, I think you're meeting with Daniel. You can,
Yep.
you're the host. You're the yeah. So we can all leave and Daniel can stay here to have the meeting.
Yeah, get the TA for this class. So that's TA for this class.
No, this is a CPSRC seminar.
Therefore, I have a question about the E20, the EC280 class. Professor left early said.
Seminar in control. Is that your point?
Yeah, yes, for EC280C, it's still assigned 4 of the 10 for the seminars, but I want to know like how he's tracking attendance here to send him a summary, but got some question about for the professor.
You can, maybe you need to send an email.
Yeah,
Yeah,
I need to, let's email him, I think. If